All right. So, we all carry around extra energy for a rainy day. Yeah. And so, look at this graph. What this graph says is fats give you the store the most energy per gram. So, if you're going to carry around extra funds for a rainy day, fats is the most bang for the buck you get. That's how you carry around your extra energy. Yeah. Now, the reason we mention this is it turns out that fats are the least dense as well. So this is a double whammy, you know. You got to carry around the extra energy, you get carried around all the time. So you want to carry around something that's light. Not only is this light, but it also gives you the most amount of energy. So that's why we store our extra energy in fats. Yeah. But here's another problem, and the reason we're talking about this is also the least dense material among all your body components. Okay. So the more fat that we have, the more buoyant we are. Okay, so if you're in water, you float. Okay, and now so we'll apply this to marine animals. Okay, so we'll look at that. So of the different body components, only fat has the density lower than water. So an average college student is about 20% fat. And our body density is 1050 kg per meter cube. Okay, that's the average density. The density of water, fresh water, is 1000 kg per meter cube. So our density is just slightly greater than the density of fresh water. Density of seawater is about 10 to the 30 kg per meter cube. You guys have seen pictures of people in the Dead Sea? Yeah, the ones that float. So the density in Dead Sea, it's the salt concentration is higher than that. So everybody floats. Okay. All right. So let me remind you of what will float. If the density of the object is less than the density of the fluid, then the object will float.
Density less than an object?
The density of the object has to be less than the density of the fluid. Then the object will float. If the density of the object is equal to the density of the fluid, it will neither float nor sink. So it'll remain. If you put it underwater, it'll remain there. For an object to sink, the density of the object has to be greater than the density of the fluid. Yeah. So let's apply this to people. So our density is greater than the density of fresh water, so you would sink normally. But if you take a deep breath, you could reduce your density to less than that of water. Okay, so you take a deep breath and you don't panic, you can't float. Okay? So you just have to stick your nose outside water. Okay? All right, let's apply this to marine animals. Okay, let me remind you, so my body fat is about 20% on average. Look at this guy. This guy looks fat.
That's not fat, that's power.
That's fat. Look at him. His typical body fat is 7%. Same as of a Usain Bolt. Okay? See, this guy can't carry too much fat because he would float and all his food is on the floor. Okay, you would have to spend energy getting down to the floor. So too much fat would make them less dense than water. That would increase the energy needed to dive. Everything in life is optimized for energy. Okay? You don't want to waste energy unless you have to. Okay? So, and here's another amazing fact about manatees. When you breathe in and out, you're only expelling about 10% of the air in your lungs. a manatee can exchange about 90% of the air in their lungs. Okay, so every time they get 90, so they're getting total almost all fresh air, which has a lot of oxygen. And this high efficiency allows them to be submerged for up to 20 minutes while resting. Okay. All right, here's another thing about manatees. So that's their lungs. Okay, so this is the side view of their lungs, and this is the front view of their lungs. So the lungs are right below the spine. This is the right lung, there is the left lung. Yeah. So there's the lung. And the reason for this design is, okay, so here's what happens. If they can control the amount of air in these lungs on the side, and they can independently fill these lungs. So if you just want to fill this lung, just open the appropriate nostril or whatever. For us, it doesn't matter where you breathe from, air goes in both the lungs equally. Yeah? So these guys can fill lungs like that independently. Well, why do they do that? Also, if there's air here, more air here, they can move it there and so on. If there's more air here, this side is more buoyant and they can roll that way. If there's more air here, this side is more buoyant, they can roll that way. What do you do when you want to dive to go food hunting?
Let the air out.
You move the air from here to there. This side becomes more buoyant, then you're ready to dive. When you want to rise, what do? Move air from there to there. You rise up. Okay? So manatee lungs are flattened, elongated, and run horizontally along their back. Okay? So all biology knows physics well. Manatees can adjust the amount of residual air in their lungs to achieve neutral buoyancy. What does neutral buoyancy mean?
They're just suspended in the water.
You're right. So they can match their density by the amount of air to the density of water. That way, they can be like that anywhere and not have to spend energy. Okay? So that's neutral buoyancy. So they can adjust the amount of air to match their density to the density of water. They can also move air from one lung to another to roll. You move air from here to there, and then you can roll that way. From the top of the lungs to the bottom to tip forward to dive. So from here to there, and then you can tip forward and dive. Okay? They can control the air in each lung separately to precisely adjust their position and trim. So they're pretty special. Okay. A typical fish has the same density as our body does. Okay. Again, this density is higher than the density of water, and so if it did nothing, it would sink. So if it wanted to be in the same position in the water, it would have to spend energy. And you don't want to do that. Okay? So how do you control that? Okay, again, how do you maintain neutral buoyancy? If you have, these guys don't have lungs, so what they have is air sacs called swim bladders. Okay? All fish have swim bladders. For ocean fish, so there's the density of fish, and the ocean density is that, and freshwater density is 1,000 kg per meter cube. Okay, so for neutral buoyancy, if you're living in freshwater, there's a lot more adjustment you have to do. You have to match this, you have to reduce this density to that density. But if you're living in ocean, you have only got to reduce this density to that density for neutral buoyancy. Okay, so freshwater fish have larger bladders, swim bladders. Okay, for freshwater fish, the bladder volume is 5 to 7%. For ocean water fish, it's only 1 to 3% of their body volume. Okay. Again, that's for neutral buoyancy, so you don't have to spend energy to hover, so to speak. All right, this is just something to see if you remember Archimedes' principle. What does Archimedes' principle say? Anybody remember that? Okay. If something is floating, okay, here's the weight of the object. So why is it not sinking? A buoyant force. Okay. So if something floats, it's not sinking. That means the buoyant force is exactly equal to that, is equal to the weight. And so the net force on it is 0 and it's not falling down. Mr. Archimedes told us that how large this force is. Okay. How large is this force? That force is equal to the weight of the displaced fluid. Okay. So that object displaced this much fluid, and the weight of this much fluid is equal to this buoyant force. Okay. And again, why do you have buoyant forces? Because the pressure in the water, in fluid, increases with depth, and the increased pressure is what's pushing it up. All right, so now let's apply this to something that you see every day. An ice cube is floating in a glass of water that is filled to the brim. Okay, so I guess I will want to erase. Oh, there you go. That was pretty good. There. Now we fill the water to the brim. Okay. Now the question is, when the ice cube melts, what will happen to the water level? So when the ice cube melts, will the water overflow?
Yes, because there's that much more of the ice mass.
No,
once that
because the
melts.
displacement's already been counted for.
So exactly.
Only what's inside of it, right?
No, so okay, the weight of this ice cube is equal to the weight of this water. And when this ice cube melts, it will become this much water. Exactly that much water. So the water won't spill. No. All right. So you guys all know that we mentioned this before. DeLand is the skydive capital of the world. And what's that? DeLand, yeah. People come from all over the world to skydive here. Many people from South America. And, okay, so when you're free falling out, spread eagle, then your terminal speed is about 120 miles per hour. When you're free falling in a nosedive, then your terminal speed is about 180 miles per hour. Okay. Now, let's say if you drop a marble in your pool, it will eventually reach terminal speed. But in water and fluids, the terminal speed is very small. Okay. Now, we're talking about this because we'll look at an example where, many animals live in the water world, in marine life, and when they die, they'll fall to the bottom. So they're falling at terminal speed, and we'll look at how long it takes them to fall to the ground, to the ocean floor. Okay? That's one of the examples we'll look at. Okay, all objects have buoyant forces, okay, acting on them, and we just learned that the buoyant force is equal to the weight of the water displaced. Here's the weight of the object, okay, and as an object falls faster, there's a drag force which depends on the speed, but eventually this force plus this force is equal to that force, and now it's not accelerating anymore, it's going at constant velocity. That's the terminal speed. Okay, so this plus this is equal to that. So drag plus the buoyant force is equal to the weight. Okay, so, and then I'll bring this over there. So weight minus the buoyant force, weight minus the buoyant force is equal to the drag force. Okay. So there is the drag force at terminal speed. It's just weight minus the buoyant force. The weight is written in terms of the densities, okay? So that's the density of the object. Again, you don't have to worry about all the formulas. So this is the density of the object, this is the density of the fluid, this is the volume of the object, this is the acceleration due to gravity, okay? All I want you to understand is the following. The density of most objects is not too much greater than the density of fluid. So this is a small term, this is a small term. That means drag forces can't be too large. What that means is terminal speed can't be too large. Okay, so when you're falling in fluids, your terminal speed is very small. You're not going at 180 miles an hour. Okay, okay. So it'll be very small, and we'll see that. We'll see an example. Okay. Now the drag force depends on the speed, like I said. Okay, for large objects, the drag force depends as the square of the speed. You double the speed, the drag force quadruples. Okay? Again, you don't have to remember any of these formulae, I'm just telling you. So for large objects, the drag force depends on the square of the speed. For small objects, it depends on the speed. Okay? There are two kinds of forces that come into play: inertial forces and viscous forces. When inertial forces are large, then this is the formula for the drag force. When viscous forces are large, are the predominant force, then this is the drag formula. Okay, so when inertial forces dominate, drag forces are proportional to speed squared. That's the formula. When viscous forces are important, drag is proportional to the speed. Okay, again, for large objects, this is it. For small objects, this is it. I guess so. So as a rough rule of thumb, objects smaller than about 100 micrometers, the size of a cell, a typical cell, is about a micrometer. Okay. So 100 micrometer fall in water with viscous drag. This is the formula. Okay. Now, while objects larger than a few millimeters experience inertial drag, they experience this drag. There's no simple expression for drag for in-between cases. Okay. All right, so here's a phytoplankton. What is a phytoplankton? Yeah, so it's a small microorganic, small plant that lives in.
It'd be hard to say, by the way.
Yeah, yeah. So phytoplankton, coccolithophores. Okay, so here, these guys have to be respected. Look at what they do. So phytoplanktons obtain their energy through photosynthesis. Okay, well, where do we all get our energy from? Where does the biome gets its energy from? From the sun. That's our first source of energy. Okay, and what locks that? So what is at the base of the food chain? Things that can absorb sunlight and convert it into chemical energy. That's at the base of the food chain. Okay. So these phytoplanktons that are microorganisms obtain their energy through photosynthesis, just as trees and other plants do. They live in well-lit surface of layers of ocean and lakes. So they're living in the top layer of the ocean, okay, where sunlight reaches them. They can trap approximately 5 to 6% of the solar energy that strikes the ocean surface. Do you guys know how much solar panels can do? Solar panels, what do solar panels do?
They trap and store solar energy.
Yeah, they absorb solar energy and convert it into electricity. Okay, and solar panels are about 20% efficient. So these guys can convert about 5 to 6% of the solar energy. Okay. So,
They can,
so they trap about 5 to 6% of the solar energy. So for every dollar that's raining down in solar energy, they pick up 5 cents. That's what that means.
Well, considering your single cell organism, that's a fair amount of solar energy that they're getting hand up.
I haven't even gotten to the punchline. Okay, so these are absolutely amazing. Okay, so solar energy is converted to chemical energy. Again, this is the base of the food chain. So we depend on all this. Okay? Phytoplanktons are key players in the global carbon cycle. They account for half the global photosynthesis activity. Okay, and at least half the oxygen production. So half the oxygen production on the planet is due to this phytoplankton. Okay? Despite amounting to only 1% of the global plant biomass. They're only 1% of the plant biomass, and they're contributing to 50% of your oxygen. Okay? All right, so these guys are phytoplanktons. Yeah. And, they die. So where do they live? They live on the surface of the ocean. The ocean is about 4 kilometers deep on the average. 4 kilometers is 2.5 miles. Yeah, so you have a rough idea of 2.5 miles. I don't know this campus too well. Well, I was going to say it's way past. From here to that road is about a mile, that big road.
The main road.
Yeah, the main road, whatever it's called.
From here to Howland, about a mile, so I would say from here to.
From here,
Here to Enterprise is about 2.5 miles.
from here to I-4 is also 2.5 miles about.
Up there, yeah.
Yeah, so that's how deep the ocean is. Okay, so this guy, after it dies, has to fall to the floor. Okay. By the way, this guy provided, while he was living, he provided you oxygen, half your oxygen, and then after he dies, after millions of years, he becomes oil. Okay, so he does well for us. Okay. So he is about 30 micrometers in diameter. His mass is 24 nanograms, and after he dies, he's got to fall 4 kilometers. Okay, so he's small, and his drag force is 6 pi eta v, and there's one more term, rv. R is his radius. Okay, so his drag force is proportional to his speed. Okay, again, you don't have to go through any of these calculations. You just have to remember sort of the numbers. Well, at least know where to look for the numbers. Here's the volume of it. Here's the density. See the density of this guy? This guy is 1700 kg per meter cube. What is the density of seawater?
1,050.
1030. So his density is greater than the density of the fluid, so he will sink after he dies. Okay? So the density is greater than seawater, so the coccolitho force will sink. All right. Again, so here's the terminal speed, here's the drag force, and that's equal to that. Again, you don't have to worry about any of these calculations. So they calculate the terminal speed. When you skydive, your terminal speed is 120 miles an hour. When you dive spread eagle like that, it's 120 miles an hour. Okay, so the terminal speed of these guys is 0.2 millimeters a second. 0.1 millimeter is that, 0.2 of a millimeter per second. So that's how fast they're falling. Yep. At this speed, to fall to the ocean floor, it takes them 240 days. That's right. Okay? So almost 9 months. Yeah. All right.
Slow trip.
Yeah, it's a slow trip. But who's in a hurry, right? I mean, you're dead, and then you have millions of years to turn yourself into oil, right? So, but anyway, so that's what goes on. Mhm. And there's plenty of them, right? And they're an important part of the energy food chain and the carbon cycle. All right, now we'll talk about a different thing, surface tension. Okay. So let's say this is a water droplet. Okay. Now, see, in water, there's a strong force between these molecules. Here's the reason why. See, oxygen is greedy for electrons. Okay. When it binds with the hydrogen atom, it tugs on the electrons, the hydrogen shares an electron with this, but this guy is greedy, so he pulls the electron more closer to him. So it turns out that the hydrogen is more positive. It's the center of positive charge is there, and the oxygen is more negative. Okay? Even though overall this molecule is neutral. Okay, so the center of negative charge is here, and the center of positive charge is here for this. Now this positive charge will attract this negative charge, this negative molecule. And this is a hydrogen bond. Okay? And it's not as strong as this bond, okay? But it's fairly strong. So water molecules attract each other. Okay? And here's the strength of this hydrogen bond. It's about anywhere between 1 to 40 kilocalorie per mole. What this means, a mole is an Avogadro number. You guys know Avogadro number? Anybody know Avogadro number? Who doesn't know Avogadro number? If I write it, maybe you'll know it. Per mole. Okay, so let me tell you about Avogadro number. All right. So you see, so this bottom number, 16 for oxygen, that's the weight of the oxygen. Okay? The bottom number, it's slightly different. That's because it has isotopes. But 1 is the number, it's the atomic weight of the oxygen. Okay? So 16, water has 2 hydrogen atoms, 16 plus 2, 18 atomic units. Okay. So H2O, so the weight is 18 atomic units. Okay. Hydrogen has his mass is 1 atomic units, oxygen has 16, 16 plus 2 is 18 atomic units. If you take 18 grams of water, you will have this many number of water molecules. This we'll call this 10, that's 10 to the 24. 18 grams of water is a trillion water molecules. So when you take a gulp of water, you just drank a trillion water molecules. I guess. So that's what Avogadro number is. This is methane. Okay. Methane. Carbon is 12. Its atomic weight is 12. Plus 4, 16. 16 atomic units. That's the molecular weight of methane. So if you take 16 grams of methane, how many molecules do you have? You have that many molecules. So that's what the Avogadro numbers tells you. Okay. So you per mole. So if you take the weight of this molecule in grams, you have 1 mole of the substance. Okay. All right, anyway, so in water molecules, these water molecules attract each other strongly. Okay, so what does that do for us? Okay, so let's look at this water droplet. Okay, so if you have this water molecule inside, this water molecule attracts him, this guy attracts him, this guy attracts him, this guy attracts him, this guy. But you see, what is the net force on this water molecule? What is the net force on this water molecule?
Conceit.
Huh?
I was joking, I said conceit.
0, because he's being pulled equally in all directions. So if this water molecule is inside the glass, the net force on him is 0. Bless you.
Thank you. Sorry.
How about this guy? This water molecule, this guy is being pulled in this direction, this direction, this direction, this, but no pull in that direction. So there's a net force downward. So if a water molecule is on the surface, okay, so let's say look at a glass of water, all these water molecules are being pulled down. Why aren't they going down? Well, there's no space to go. Okay? Somebody's got to be on the surface. Okay? So it's like if a molecule is on the surface, it's being pulled that way to be on the surface. Okay? So a liquid surface is like a stretched rubber band, rubber sheet. It's under tension. Well, am I making this up? Look at this.
No, anyone whose belly's electrical cool knows that surface tension is real.
Yeah. So it can actually support a weight. Okay. Now, the only way you get in there is if you break the surface. Okay? So that's surface tension. Okay. So a liquid surface. Okay, and stronger the attraction, greater will be the surface tension. Okay. So now we'll see why we're talking about this. So surface tension is a property of the liquid surface that has it behaving like a stretched elastic membrane. It's caused by the cohesive forces between liquid molecules, again, between the attractive forces of the liquid molecules. So between the attractive forces. Molecules on the surface are pulled downwards and sideways, creating an inward force that tightens the surface. So the surface tension of water is a result of the strong hydrogen bonds. And here's a way to measure this surface tension. So this is a wire contraption. You can take water and pull it there. So what happens is these water molecules are attracted to the wire, and these water molecules are being pulled by their neighbors in that direction. So you have to apply a force to balance this force. Okay. And you can imagine longer this line of molecules, greater the force you have to apply. So just to hold this wire there, you have to apply a force. What do you think will happen if I let go of this force? It'll snap back. Okay. So surface tension is, okay, this force that you have to apply, which is equal to the tension, and well, this tension depends on the length of the wire. So what we'll define as surface tension surface tension is denoted by gamma, and it'll be equal to this tension divided by the length, since it'll depend on the length. Okay? So this is the surface tension. And surface tension for water is high, meaning that surface of the water is like a tight, stretched rubber sheet. Okay? The liquid pulls on the wire with the tension-like force, rather like a stretched spring. The forces are balanced when the wire is held in equilibrium. Okay? So measuring the pulling force is a way of determining the tension. So when you measure, when at rest, this force is equal to the force with which the water is pulling back, or the liquid is pulling back. So surface tension denoted by gamma is the tension divided by this length. Okay? So even though the name is given a tension, oh, this is tension. So surface tension is tension divided by length. Okay? Surface tension is the tension per meter of contact. So its units are Newton meter. All right, so we talked about the hydrogen bond. Okay, so surface tension is what allows these are water striders. Okay, bubbles and water drops assume a spherical shape. So if you if you've seen raindrops falling, all the drops are spherical. Okay, so why is a raindrop spherical?
Because it's all being forced by the center.
So what happens is, for a given volume, the smallest area is that of a sphere. The smallest surface area is that of a sphere. So you can take the same volume of water and flatten it out. This has a greater surface. Okay, and remember, it costs you energy to put the molecule on the surface. It costs you energy to have a surface. Okay, so since a sphere has the smallest surface area, so all droplets are spherical. So that's when you're small. And if you get too big, then you have to flatten out, because then you have to account for gravitational potential energy as well. Okay. So bubbles and water droplets assume a spherical shape. Insects walk across water, and so these are all proofs of surface tension. And liquids rise in a capillary tube, and we'll talk about that in a second. These are manifestations of surface tension. So I don't know, we are in the healthcare industry, so you might sometimes see blood draws. So you prick your finger, and then you stick a small pipe there, a capillary tube, and blood is drawn into the capillary tube. Okay. You guys seen this?
Yeah, I've had it done.
Okay. So you don't have to pull on the capillary tube. You don't have to suction it, okay? Blood will flow in it. And I'll show you a problem related to that. So many biological processes, from functioning of alveoli in the lungs to extraction of water in the soil by roots. So in soil, water rises to the top by the capillary effect. You have used paper towels, and the way paper towel gets wet is water rises, flows in the capillary tubes. Okay? So, all right. So here are water striders. Are insects known for the ability to walk in water? The feet on a strider are hydrophobic. Hydrophobic meaning they repel water, or at least they're not attracted to water, due to thousands of microscopic hair that enable the feet to push the water down like a dimple. Okay. So now here's, so just to illustrate a calculation, so here's a needle. Have you seen a needle floating on water? Okay, so if you can take a needle and take a pair of tweezers and carefully put it on top of water without breaking the water surface, and you can float a needle on the surface of water. So go try it. Okay, so you have to have flat tweezers, flat-headed tweezers. All right, so when the needle is on the surface of water, see the rubber sheet bends like that. This is the surface tension, okay? And this component of the surface tension is balancing the weight of the needle. Okay? And that's how this water strider is also walking. Okay? So you can think of these as four needles. There's upward forces on them, and that's balancing the weight of this guy. Okay? I tried this. Unfortunately, I'm too heavy to walk on one. All right. So it turns out that T sine theta is this component again. You don't have to know the math. So twice of that is balancing the weight. And the tension is surface tension times the length. Surface tension times the length. Okay. So if you calculate all of this and if you calculate the mass, the maximum mass of the needle that will be supported is 2 times the surface tension times this divided by G. And the maximum weight corresponds to when this angle becomes 90 degrees. And that becomes 1. So anyway, so a 4 centimeter needle, almost an 1.5 inch needle, the maximum weight that can be supported is 0.6 grams. Okay, so that's what that calculation says. The weight of the needle, a 2-inch needle, if it's about 0.6 gram, you can support about a 0.6 gram needle. Yeah. Here is the surface tension of various material. Water. Look at this soapy water. The surface tension has decreased. Now this is an important fact. Okay. So remember, the surface tension of water was because of the strong bonds between the water molecules. Okay, the hydrogen bond between the water molecules. Now if you add soap to the water, this surface tension decreases by almost a third. That's an enormous jump, and that's important. So what do you think might be happening? So here's what's happening. Soap molecules get in the way and they weaken the net effective force between water molecules. And that's how they reduce the surface tension. Yeah. Now in our alveoli, okay, the surface tension is high, and we'll come to this in a second. And if the surface tension is too high, then you can't, it's like a stiff balloon, you can't blow this up, balloon up. So you would have trouble breathing.
Is that why the alveoli are coated with, like, I guess for lack of a better word, they have coating on them, so that it has the stretchability?
Right, so there's some kind of protein, a lipid, that gets in their thing. It's like soap, and it reduces the surface tension. It makes them less stiff. And now you can blow up the alveoli easier, and you can breathe. So some newborn kids, preemie babies, don't have these proteins. And so now they have a hard time breathing. Okay? So what they do is they provide these surfactants. So surfactants to soften their alveoli. Okay, adding a surfactant such as soap reduces the cohesive forces, which decreases the surface tension significantly. Okay, so we'll come to that. This is of supreme importance to mammalian lungs. Surface tension also decreases with increasing temperature. That's the reason why hot water cleans better than cold water. Okay. So what you want is when we clean, what we want is, see if the water molecules attract each other strongly, the water won't stick to the stuff that you want to clean if they're attracting each other strongly. If you want the water molecule to stick to that stuff, that force to be greater than this force for it to clean. You know? All right, now let's look at a bubble. Okay. What happens is, so here's a bubble, let's say a soap bubble. Outside, the atmospheric pressure is P0. Okay, that's the atmospheric pressure. What happens is, okay, so now look, it's a bubble. So this is like a stiff balloon. So the balloon wants to contract. Okay, so what it does is it increases the pressure of air inside. The air pressure has to be greater than the outside pressure because the air has to push this because this bubble wants to contract. Okay. All right, so this pressure inside is greater than the outside pressure. Okay. inside all bubbles. All right, so the increase in pressure, so the inside pressure minus the outside pressure, for a bubble, for a soap bubble, is 4 gamma divided by R. Okay? Now, if you're a drop, so if you're an airdrop in water, that inside pressure to outside pressure is that, 2 gamma times R. Okay? Now, alveoli, so again, we're talking about all this. Alveoli is like an air bubble, and the lung is surrounded by interstitial fluid. So an alveoli is like an air bubble in water. Okay? And so the excess pressure inside your alveoli is 2 gamma divided by R. Okay. All right, we'll use this. All right, so inside a bubble, so let's look at 2 balloons. So here's 2 balloons, and the excess pressure inside a balloon is 4 gamma divided by R. This is surface tension, and this is the radius of the balloon. Okay, so what happens here? I have 2 balloons. This balloon is obviously smaller. They have the same surface tension, meaning they're made of the same rubber. And now I've connected the 2 balloons. What do you think will happen?
I think-
Oh, sorry.
That's fine. I think B will go into A.
So B will go into A? Yeah, you're right. So you see, gamma is the same for both the balloons. R is smaller for B. So the pressure here is higher, and air will move from here to there. So the smaller balloon will collapse, and all the air will go there. Okay? So that was very good. Okay, so let me show this to you. Video unavailable. Okay. All right, maybe you guys are out of luck. What's going on?
YouTube is not working.
Oh, is it? Okay, so,
Just look, because yours was loading, so I don't know if it was the channel or if YouTube just needs to.
all right, we struck out on 3 tries. Okay, why do we care about this?
How our lungs work. Our lungs are essentially 2 balloons.
So our lungs have 500 million alveoli. You're not going to make them all exactly the same size. 500 million alveoli. Okay, so if somehow one alveoli got bigger than the other, all these guys would collapse. Half, they're all interconnected. Half of them would collapse, then the next half, then the next half. Before long, you
Lungs
don't.
don't work anymore.
Yep. How do you fix that?
Use strengthen A so that it doesn't, so that the pressure is even with B.
Very good. So, bigger the radius, you somehow have to figure out a way to make the balloon stiffer. You have to make this bigger. So this number stays the same as for the small one. Did you guys understand that? So bigger the balloon, you want to make the surface tension higher. All right, so let's see how the body fixes this problem. So your body is amazing. Okay. So what you have to do is, as the balloon gets bigger, you have to increase the surface tension, and as the balloon gets smaller, you have to decrease the surface tension. All right, did you guys understand that? So you have to automatically, the larger the balloon gets, the stiffer you want to make it, The smaller it gets, the softer you want to make it. All right, so let's fix that problem. Okay, so here's the alveoli. What we'll do is we'll throw in 100 proteins each. 100 of those protein molecules, surfactant molecules. Okay. What do the surfactant molecules do? They make the things softer. They make the walls softer. Okay, because the surface tension of pure water is higher. The surface tension with the surfactant is lower. Okay. Now, when the balloon is bigger, the 100 surfactant molecules are spread over a larger area, so this guy is stiffer. When the balloon is smaller, when the alveoli is smaller, the same number of surfactant molecules, the concentration is higher, the surface tension is lower. Okay, so you have a fixed number of lipid molecules in there, surfactant molecules, and it automatically does this job for you. Gamma is surface tension, so the concentration of surfactant is lower in bigger molecules, it becomes stiffer. So there's a built-in mechanism for the alveoli to get stiffer as it become bigger. And as it gets smaller, it gets softer. The concentration of surfactant molecules is automatically changing. Okay? So that's how your body fixes that problem. Okay? And this is just a number, just a problem showing you the pressure. So this is the pressure inside a drop. So let's say a drop being also an air bubble surrounded by water. So this could be an alveoli surrounded by interstitial fluid. Okay, so it shows you the excess pressure inside. Okay, so you can calculate this. So air bubbles in water. Okay, so the excess pressure for a 1 centimeter bubble, a 1 centimeter bubble is that much. 100 micrometer bubble is about the size of 100 cells, and 1 micrometer is the size of a cell. Okay, so the excess pressure is 30 pascals, 3,000 pascals, 30 pascals for this guy, 3,000 pascals for this guy, and 300,000 pascals for this guy. Okay, 1 atmospheric pressure is 10 to the power 5 pascals. Okay, so for a bubble the size of your cell, the pressure is 3 atmospheres. That is enormous. Okay. So if you took a bubble the size of your cell and you filled it with air and surrounded it with water, it should burst. Okay. So now let's come to alveoli. So here are alveoli. Okay, you have about 500 million alveoli. Okay, so you saw that. What did you have to do? You had to make sure that if one alveoli is small and another is bigger, you can't have the bigger one gets blown up and the smaller one collapse. You can't have that. Okay, and you did that by changing the surface tension appropriately. Okay, as the balloon gets bigger, the surface tension increased correspondingly, so it was harder to blow it up. Okay, so the excess pressure inside is, because the alveoli are surrounded by interstitial fluid, is that. Okay, so the excess pressure needed to inflate an alveolus is proportional to the surface tension and inversely proportional to the radius. Okay. The diameter of these alveoli are about 0.2 to 0.5 millimeters. Okay, again, a millimeter is that, and so it's 2/10 of a millimeter. That's the size of your alveoli. Okay. Why are your alveoli so small?
Because you have to pack so many of them in such a small space.
No, why are your alveoli so small?
Because of, oh my gosh, what do you call it? Like when you soak the sun in, you have to get the oxygen into your bloodstream, so you have to have a smaller space.
So your diffusion, very good.
She's gonna get it, she's gonna get it.
Diffusion, how is all molecules transported? The last mile is all diffusion. Diffusion is a slow process, and you can only travel small distances. Okay, so here's a capillary, and here's the good stuff. There's the bad stuff. That's carbon dioxide, and here's oxygen. Okay, this has to diffuse to the capillaries, and carbon dioxide has to diffuse there. Okay, so diffusion can only have they can only move small distances. Okay, we'll see in a problem later that blood passes alveoli in about 5 seconds. So you have 5 seconds, or 2 or 3 seconds, you can think of that, for this diffusion to happen. Okay, so that's why alveoli has to be small. Okay, if your alveoli was this big, this gas would never be exchanged. Okay, so you have to pass through small, tiny alveoli. So imagine this. So if the alveoli are small, then you got to you got to go by 500 million alveoli. Imagine the network of capillaries. Okay? So it's like you got to build a road around every house. Okay? Every house, there's got to be a road surrounding the house. Okay? All right. Oh, wow. Okay, so some of the breathing problems we encounter, the surface tension of water is large. Great effort would be required to expand the alveoli during inhalation, like trying to blow up a stiff balloon. Okay. During exhalation, if the number of molecules inside the alveoli decrease, creating an imbalance, the pressure force along strong surface tension will collapse again. If one alveolus becomes larger than the other, it would require less pressure to further inflate. So one alveoli would inflate more at the expense of others. So you saw that the smaller ones would collapse, and you saw how to fix that by surface tension. Okay. Now I'm going to show you how breathing happens. Okay. So these problems are avoided in healthy lungs by pulmonary surfactants, a lipid protein complex that is absorbed into the air-water interface at the surface of the alveoli. Okay? So surfactants, which are lipid proteins, make the alveoli softer. The surfactant lowers the surface tension. Okay? The lower surface tension makes it easier for alveoli to expand during inhalation. Premature infants often lack sufficient pulmonary surfactants to breathe on their own. So this is called the neonatal respiratory distress syndrome. Has anybody encountered this in your professional life or anything? So it's not uncommon. It can be treated by introducing an artificial surfactant directly into the lungs. Okay, so you just pump surfactant into the baby's lung. All right, so I'm just going to point at a number because we're sort of running out of time. This is a water bubble, and this radius is the size of your alveoli. Okay, a water bubble 5 times larger, so this is 5 times larger than your alveoli. A water bubble the size of your alveoli with the surfactant. Your alveoli has a surfactant, and its surface tension is that. Okay, so what we're going to calculate is the excess pressure inside this thing. So the excess pressure for part A without surfactant is 11 millimeters of mercury. The excess pressure for the big alveoli is 2 millimeters of mercury. The excess pressure for the bubble with the size of the alveoli with a lower surfactant is that. And this is key. Okay, so 5 millimeter of mercury. You have to remember that. Okay. So Now let me remind you. Okay, so if you want a fluid to move from here to here, air is a fluid. If you want air to move from here to here, what you have to do is you have to maintain a higher pressure here than and lower pressure here. So a fluid will move from a higher pressure region to a lower pressure region. Okay, now let's do this. So what I'm going to do is, here is an alveoli. Okay, so this is the alveoli, this is the outside. So this is bronchial, your bronchus, bronchial tube and all that stuff. Okay. What is the pressure here? This is the outside. That's atmospheric pressure.
And it's gonna be lower than what's.
Is the atmospheric pressure changing? No, it's not. So, when you want air to go in here, when you want to breathe in, what do you have to do? You have to reduce the pressure inside the alveoli. It has to be less than that. And when you want to breathe out, you have to increase the pressure here. Okay? So, you're making air move in and out by controlling the pressure here. Yep. So, in this business, we'll do gauge pressure. Gauge pressure is actual pressure minus atmospheric pressure. So, pressure minus atmospheric pressure, the gauge pressure here is 0 millimeter. 0 millimeter of mercury. Okay, outside pressure. So, when you want to breathe in, you have to make this pressure less than 0 millimeters, okay, less than atmospheric pressure. And when you want to breathe out, you have to make the pressure inside here greater than atmospheric pressure, okay? We just calculated the number for an alveoli size, that's 5 millimeter of mercury. The excess pressure due to this being a rubber balloon is 5 millimeters of mercury. Okay, the excess pressure is 5 millimeters of mercury. How the heck are you going to breathe? How are you going to bring in air? This pressure is higher than that. All air should be going up. So how does your body solve this problem? Here's
Tiny bubbles instead of big ones.
so here's a pleural cavity. This is partial vacuum. You got a vacuum pump inside your body.
What's it called again?
It's the pleural cavity. Okay? The pressure inside the pleural cavity is minus, it's 756 millimeter. There's atmospheric pressure. So it's minus 4 millimeters of mercury. So surrounding this is minus 4 millimeters of mercury. Well, 5 plus minus 4 is still 1 millimeter of mercury. That's still positive pressure. That would still drive out air. All right, so when you want to breathe in, here's what you do. You lower the diaphragm, you expand your rib cage, and decrease this pressure further. You decrease this pressure to minus 6 millimeters of mercury. So when you breathe in, you're decreasing it to minus 6 millimeters of mercury. Okay, so 5 minus 6 is minus 1 millimeters of mercury, air will move in. And when you want to breathe out, you raise your diaphragm, your rib cage goes back down, and the pressure inside the pleural cavity goes to minus 3 millimeters of mercury. Okay? I'm giving you rough numbers. 5 minus 3 is 2 millimeters of mercury. 2 millimeters of mercury will drive the air out. Okay? So that's how you're breathing. You're changing the pressure inside your alveoli. Okay? So when you breathe in, the pressure inside the alveoli is minus 1 millimeter of mercury. Remember, minus 1 just means that it's not negative pressure, it's just lower than atmospheric pressure. Air, so again, I'll draw the alveoli. This is 0 millimeters of mercury. That's gauge pressure. And when you're breathing in, you need a lower pressure. It's minus 1 millimeters of mercury. And when you're breathing out, it's plus 1 millimeter of mercury driving the air up. The interpleural pressure, which is what you're controlling to breathe, it's minus 6 millimeters. Remember, the excess pressure is 5 millimeters of mercury. And when you're breathing in, the interpleural pressure is minus 6. So 5 minus 6 is minus 1, and air comes in. And when you're breathing out, this is about minus 3. So,
So the suction that holds your lungs up also helps you to hold air in.
right. Okay, well, that's why you have this, you have to maintain this vacuum. Okay? You get in an accident and you puncture this vacuum. You can't breathe. Your lung collapses.
My kid used to get spontaneous pneumothorax.
Oh, yeah? How often?
It happened 9 times before they removed part of his lung where the blood were happening at the top. Because he's tall, thin, and white, and they said that's all the precursors, because your lungs won't hold up with the suction. So it does this, and then you get blisters up here, and then the air comes out the blisters, and
Okay, so you want to read the lungs are attached to the chest wall by liquid contact. That is by adhesive forces. Okay, the lungs are pulled open by these adhesive forces when the rib cage expands. So that was lacking in your son's. Okay. All right, so again, here's the important thing you want to remember. So you're changing the pressure inside. This pressure is not changing. You want air to move in, this has to be less than atmospheric pressure. You want air to move out, this has to be greater than atmospheric pressure. Okay, so, and your body has figured out that by creating a vacuum around the lungs. Okay? All right, that's it for today.